So hello friend, welcome again in this lecture number 9.1, Electronic Conductivity and Fermi Dirac Function. This is the part of CSBT Physics. Learn with me. A series of lectures on some special topics. So outlines of this lecture: first, objective and prerequisite, then the distinction between metals, semiconductors, and insulators. Then free electron model for solids and semiconductors will be discussed, and Fermi energy levels. The concept of Fermi energy level is very important in semiconductor physics. So this will also be discussed. And Fermi Dirac Distribution Function. This is a common topic used in unit number 8 and 9. So I am introducing this topic here. And finally, the summary of the lecture will be given place. Objective and prerequisites of these lectures. The objective of these lectures are to introduce basic classification of materials on the basis of band theory, to discuss the model for electronic conduction in metals and semiconductors, third, to locate Fermi energy levels in different semiconductors, to introduce Fermi Dirac distribution function and its analysis at different temperatures, and the prerequisite for this lecture to understand thoroughly. I expect from the student they have a basic knowledge of semiconductors, Ohm's law, equations of motion, and fundamental mathematical calculations. Now the classification of solids on the basis of band theory. So according to band theory, the electrons in the solid can possess bands of energies, that is called allowed bands of energies, and these electrons may not possess some other bands of energies. These are called forbidden bands of energies. The allowed bands of energy and forbidden bands of energies are present alternately in one after another for the electrons of a solid. The topmost band is called conduction band. This is the conduction band, and the next band below conduction band is called valence band. These valence bands actually consist valence electrons, and these two bands are separated by a gap which is known as forbidden energy gap. So on the basis of this, the value of this forbidden energy gap, this band theory of solid, materials are classified into insulators, metals are conductors, and semiconductors. So this is the first type is insulator. This is the band plot of insulator. So the valence band of these materials are those materials remains full of electrons, and conduction bands are completely empty, and the forbidden energy gap between this conduction and valence bands are widest, and the difference is more than 6 electron volt. The examples are mica, glass, ebonites, and these are good insulators. Now conductors, in the case of conductors, valence bands and conduction bands overlap each other. This is the band plot of metals. Here conduction and valence bands are overlap, and there is no forbidden energy gap. So easy, this is the notation for forbidden energy gap. It is 0. At absolute 0 temperature, large numbers of electrons remains in the conduction band. This is the property of the conductor. The resistance of conductor is very low. Large numbers of charge carriers are available here, so the electricity can pass easily through the conductors, and examples are aluminium, silver. These are the good conductors. And now in case of semiconductors, so this is in between that conductors and insulator. That's why this is known as semiconductor. The semiconductors remain partially full valence band and partially full conduction band at room temperature, and the energy gap is narrower. So this is for the band plot of semiconductor. So the examples are the conduction band remains fully empty of a semiconductor, where the valence band remains full of electrons at the absolute 0 temperature. So value of Hz is 1.1 for silicon, and it's 0.7 electron volt for the germanium, and these are well known semiconductors, and these are good conductors at room temperature itself. So it can easily overcome due to thermal excitation or light. So silicon and germanium are insulator at absolute 0 temperature, but on the other hand, with the increasing of temperature, the electrical conductivity of semiconductor increases. So now the free electron model for solids, and we will use the same model for semiconductors also. So according to this model, this theory, the metal consists of electrons which are free to move about the crystals, and like molecules of gas in a container. Mutual repulsion between electrons is ignored, and hence potential energy is taken as zero, and one can say the total energy of electron is equal to its kinetic energy. This model provides a satisfactory explanation of certain properties, just like electrical conductivity, electronic emission, electronic emission, and failed to explain that why some solids are good conductor and some are semiconductors are insulator. It also failed to explain the specific heat of metals, magnetic susceptibility of paramagnetic metals, and so on. And this is developed by Drude and Lagrange. That's why this is known as Drude-Lagrange theory. And the basic postulates of this theory is the outermost electrons of the constituent atoms of the metals are weakly bound with the atoms. Hence, these electrons get separated from their atoms and move freely inside the substance. And these are called free electrons. These electrons are as free as gas molecules. There are large numbers of free electrons inside the metals, and they behave like molecules of gas enclosed in the container. Hence, it is called free electron gas. So, these free electrons are responsible for thermal and electrical conduction inside the metal. Hence, they are also called conduction electrons. So, the free electrons in thermal equilibrium, they obey Maxwell's Boltzmann statistics. There are many statistics used in the semiconductor physics and solid state physics. So, for free electron conduction in thermal equilibrium, the Maxwell-Boltzmann statistics is used, which states that the free energy per electron at the absolute temperature T is about half multiplied by kT, where K is Boltzmann constant. Inside the metal, free electrons move randomly with high velocity, and it depends on the temperature of the metal. During the motion, their velocity and direction change in such a way that the rate of flow of electron in particular direction is zero. When the metal is kept in external electric field, the free electrons get attracted in direction opposite to the direction to the external electric field, and they start moving with the constant average velocity that is known as the drift velocity. So now we will start simple calculation, which I think a student should already perform during their 12th level physics. So when an electric field is applied between two ends of metal of area of cross section A, and force acting on the electrons in electric field, this is electrostatic force is equal to E multiplied by. When this is compared with Newtonian force, F is equal to ma, then we have this acceleration of electron is equal to A, that is E capital E by m. This is the acceleration of that electron. And then average velocity, which is known as drift velocity, can be simply calculated by using this Vt is equal to this acceleration multiplied by this tau. Tau is the time, that this is relaxation time or the collision time, one can say. So this is now have E capital E multiplied by tau by m. So this is the drift velocity. So the conductivity of metal can be related to the numbers of charge carrier present in the material. Let us consider this block of cross section area A, and length is L. So the total volume will be A multiplied by L, and this is connected with this battery. And so the total number of electrons in solid, that is N, it is equivalent to N. This is the charge density, number of electrons per unit volume, and when this is multiplied by volume, then this is the total number of electrons in that solid. So the charge is calculated as this is Q is equivalent to the total number of N multiplied by charge of electron. So this is the total charge, and simply current is defined as equivalent to Q by T. So by substituting the value of Q, we will have this I is equivalent to NEAL by T. So the current, this is the current, and this Vd, the drift velocity, it can also be defined as length upon time, and this length is actually that average path between two collisions of electrons, and this is that tau time. So J is equivalent to I by A, the current density. So J is equivalent to NEVD. So when we substitute this I here, A is just cancelled out. So we will have this current density. So again, from Ohm's law we have I is equivalent to V. So we have just to play with different physical parameters related to electrostatics, that resistance, current, voltage, electric field intensity, and related terms. So I is equivalent to V by R from Ohm's law. So V is equivalent to, V can be written as equivalent to that V, and the resistance R is equivalent to this is that terms related to resistance. So one can write this is equal to sigma AE, where 1 upon rho, that resistivity, is defined as the conductivity. So sigma multiplied by A, and V upon L, V upon L can be written as equivalent to electric field intensity. So this current density J can be also written as equivalent to sigma E. So by comparing these two, one will have this sigma is equivalent to the J is equivalent to NE square E tau by M, where this Vd is replaced by E tau by M. So this is current density J. So just by comparing one equation to another equation, we will have this formula for the conductivity, that mobility, with the sigma, that conductivity is equivalent to NE mobility. So just student have to play with these parameters, and this can be easily formulated. So in case of semiconductors, the conductivity is because of that electrons and a hole as a whole. For n-type semiconductor, this is the electrons are a majority charge carrier, and in p-type semiconductors, holes are majority charge carrier. And a simple semiconductor, that is the intrinsic semiconductor, this will be the sum of electrons and hole. So that current density J can be written as equivalent to, this part is related to electrons, so conductivity due to electrons, and this part is related to conductivity due to hole. So this conductivity is equivalent to N E mu E plus that P, the number of, this is the density of holes, and N is the density of electrons, and the charge is same E, and this is the mobility of hole, and this is the mobility of electrons. So we will use to get the conductivity of that semiconductor by using this formula. Now another interesting topic, that is the Fermi energy level. This is related to semiconductor physics. So this Fermi energy level is actually related to the distribution of electrons in different energy levels. In solid crystals, free electrons possess different energies. So this is actually the quantum mechanical phenomena where we just think about discrete energy levels. So in solid crystal, the free electron possesses different energies, and according to quantum theory, at absolute zero of temperature, the free electrons occupy different energy levels continuously without any vacancy in between field state. This can be understood by dropping the free electrons of a metal one by one into the potential well. So this potential well is compared with that one electron inside a box. So the first electron drop to occupy the lowest energy value. So this is the lowest energy value. So the first electron will occupy this, the second will occupy this, and by using that Pauli's exclusion principle, the third electron drop would occupy the next energy level. That is the third electron drop would occupy the energy that is greater than this. E1 is greater than E0, and this is because of Pauli's exclusion principle. So this term is very familiar terms in chemistry. So if we have a metal containing n even numbers of electrons, they will be distributed in first n upon 2 energy levels, and the higher energy level here, let's say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we have 24 electrons, and these 24 electrons are distributed in 12 energy levels, and the highest energy level, this highest energy level is filled at 0 Kelvin, is known as Fermi level. So the highest in filled level, which separate the filled and empty level, these are the filled levels, and above levels are, these are the empty levels. So this is separating that filled levels and empty levels. So this is known as Fermi level, and corresponding energy, this is known as Fermi energy. So the energy can also be defined as the highest energy possessed by the electrons in the materials at 0 Kelvin, and at 0 Kelvin the Fermi energy EF is also represented somewhere in EF0, EF0. So These are the distribution of electrons in different levels. Now for the Fermi level for intrinsic semiconductor. So intrinsic semiconductors are pure semiconductor, and this is the valence band where all electrons are valence electrons are here, and conduction bands are empty, and there is a forbidden energy gap in the range of 0.7 electron volt in the case of that germanium, 1.1 in case of silicon. So when temperature increases, some of electrons can just transfer from valence band to conduction band, and these are the conduction electrons, and this is because of thermal excitation also. So this is for the pure semiconductor, and the position of Fermi energy level is just in between this conduction and valence band, and for the detailed calculation, the detailed calculation will be performed in lectures, how that Fermi energy level is just in between this conduction band and valence band. So the Fermi semiconductor will be able to show some electrical conductivity as the temperature increases. Now the Fermi level of extrinsic semiconductor, that extrinsic semiconductors are divided into N-type and P-type semiconductor, and it is depending on the impurity added. If the pentavalent impurity is added, we have that N-type semiconductors, and when that trivalent impurity is added, we have then P-type semiconductor. In N-type semiconductor, that electrons are in the majority as a majority charge carrier, and in P-type semiconductor, that holes are majority charge carriers. So at thermal excitation, it's just the conductivity of electrons and hole increases. So as far as that Fermi energy level, the position of Fermi energy level is concerned, so this is that band diagram for N-type semiconductor, where this Fermi energy level is shifted towards this conduction band, because we have excess number of electrons here in valence band. So the probability of existence of electrons, that is more towards this conduction band. So this Fermi energy level shifted towards this at room temperature also. Whereas in p-type semiconductor, in the valence band, some holes are there which just recombine some electrons, and one can say the probability of existence of electrons is shifted towards this valence band. So one can say this Fermi energy level is shifted towards this valence band in case of p-type semiconductor. So as a summary, we can say in N-type semiconductor, the Fermi energy level is shifted towards conduction band, and in p-type semiconductor, it is shifted towards the valence band. And in case of pure semiconductor, in intrinsic semiconductor, that Fermi energy level is just in between the conduction and valence band. So this is one special topic. Now that Fermi Dirac distribution function, actually that the distribution of electron is quantum mechanical phenomena, where we talk about that probability of existence of an electron or any particle at a particular energy level. So now after that, the concept of Fermi energy level, we will discuss about Fermi Dirac distribution function. So this, the probability that a particular quantum state of energy E, again that probability. So the probability that a particular quantum state energy is filled with an electron, this is given by Fermi Dirac distribution function. So this is quantum mechanical phenomena. So we will talk about the probability, and this is that expression f, the function of energy, it is equivalent to 1 upon 1 plus exponential of E minus EF by kBt, where kb is a Boltzmann constant. So here this E is that energy level where we want to get the probability of existence of any energy, and EF, that EF is that Fermi energy level. So this is a graph between that Fermi function, that the Fermi Dirac function, and that energy, and this point is Fermi energy level at zero temperature. So at a different temperature, where T1 is less than T2, which is less than T3, and that T is equivalent to 0 Kelvin, we have this type of plot, and mathematically we can see like this. So at T is equivalent to 0 Kelvin, when this E is less than EF, then the value of this Fermi function will be 1. and if this E is greater than EF, that will be 0. Just let us see. If this is this E is less than EF, this will be a minus term. When it is multiplied by divided by 0, so this will be exponential of minus infinite, and that exponential of minus infinite is 0. So 1 upon 1 is equal to 1. Whereas when this E is greater than EF, then this will be a plus infinite, and plus infinite exponential of plus infinite is just infinite, so 1 upon infinite is equal to 0. So we have that stepping like curve for t is equal to 0 is because of this. Now, so the curve have step like characteristic for f is equal to 1 for energy below this, and f is equal to 0 for energy above this. This represents that all the energy states below this Fermi energy level are filled, and whereas the those above are empty. Now at t is greater than 0 Kelvin, so this Fermi function is less than 1 for E is greater than E is less than EF, and it is greater than 0 for E is greater than EF, and this is half when this E is equal to EF. So just by putting this value, this function gives some parameters like this. So these are just a summary of this Fermi Dirac distribution function. As the temperature is raised from the absolute 0 to T1, the distribution curve begins to depart from the step-like function. So this step-like function is only for that T is equal to 0 Kelvin. As temperature increases, that distribution curves begin to depart, and it tails off smoothly to 0. Again, with the further increasing temperature to T2 and T3, the departure and the tailing of the curves increases. This indicates that more and more electrons may occupy higher energy states with an increase of temperature. When we increase the temperature, more and more electrons may occupy higher energy, and as a consequence, the numbers of vacancies below the Fermi level increases, because that electron is transferring from lower energy level to higher energy level. So obviously the vacancies will be created in some portions of that lower energy levels. At non-zero temperature, all these curves pass through a point whose this epsilon, that is equivalent to 1 by 2. This is that Fermi energy level. So EF, this lies halfway between the filled and the empty state. So this Fermi energy level is filled in. This is just a boundary between filled and empty state, and this is for every temperature. So now the summary of this lecture: the basic classification of materials and the basis of band theory was introduced. On the basis of that, the value of EZ. The model for electronic conduction in metal and semiconductor. So Drude model was discussed for metal. This is also the part of unit 8, and this is that simple formula is used for semiconductor here. Now the Fermi energy level is semiconductors were analyzed. So for that intrinsic semiconductor, that Fermi energy level, which actually gives the probability of existence of that electron at 0 Kelvin, that maximum level. So this is just in between that valence and conduction band, whereas in case of n-type semiconductor, it's shifted towards conduction band, and in p-type semiconductor, it's shifted towards valence band. The concept of Fermi Dirac distribution function, this is also introduced in this lecture, and it is analyzed in details at different temperatures. So thank you all, and some calculations related to that conduction of electrons inside the metal semiconductor, as well as that Fermi Dirac distribution function will be continued in that green board level derivations. Okay, thank you all. Enjoy learning.